Yeah, so when you slice off this mountain in an arbitrary direction, so I walk. So how do you find? So then you get a curve. So this is a curve on this plane. So so if you have this curve and then the derivative, or we want to find the tangent to this curve at a certain at this point P. So P is given, P is P comma A comma B, yeah. So P is here, right? And we know the direction is given, right? This is known and this one is known, yep, right. Then, then how do you find the gradient to this curve at this point? So, which is called the directional derivative, right? Directional derivative at this point. So now we are going to calculate the directional derivative at this point, okay, in this direction. So direction is given, point is given, right? So now we are going to find the directional derivative of the function in this direction at this point, right? Okay, how do you find that? For that, you have to find the, so this is the projection, OXY projection, right? OXY plane projection, right? So here you see the contour map as well, this direction. The traveler moves along this path. If the traveler moves along this path, we won't find the slope, his path at this point. Yep. So for that, you need to find the vector equation of this straight line. So very easy to find because you know this point P is given. P is is this coordinate A comma B, and the direction is also given. Is this one. Then if you know a point and the parallel vector, then this straight line is passing through this point P, and which is parallel to this vector. Then you know how to write the vector equation of this straight line, which is this one. And here t is a parameter, right? T is a parameter. Then you get all points on the straight line, right? Okay. Okay, let's see. So this is t. If you want to find the slope, yep. So you have to consider delta t. If you change t variable by, so initial t is this, this is the point, p is the point. So if you consider infinitesimal change delta t, then the next then your xy coordinate changes to u, coordinate changes to, so a plus, yeah, del, no, let's see, this one, delta t, that's right. A plus delta t u, delta u, u1, x1, x component, and the other one b plus delta t u2, so here we can see, let's just, so here you can see if you move, if you consider delta t change, right, from here to there, right, so the original position is p. If you consider small change to this variable delta t, right, then the x and y changes in this way. X coordinate changes to a plus u1 delta t, and y coordinate changes to b plus u2 delta t, and the corresponding function value is yeah, this is the height actually, right? F of A comma B, right? You get height at this point, right? And the corresponding height is this, right? Then you can find the vertical difference, height difference, if you move from here to there, right? So you can find the vertical difference here. This is the difference. So earlier his his height is f of a b, and if he move in this direction, so this is the projection, right? OXY projection in this direction. Yeah, his height changes to this. Then the difference between these two heights is the change in z direction, delta z, right? So difference between these two heights. And you can use tail expansion for several ways. So this is the tail expansion for higher dimensions, right? You don't need to prove this. Yep. Yeah. So tail expansion of this one is you can ignore higher order terms of the tail expansion. This is approximately equal to partial sum of this with respect to x evaluated at this point times this variation and plus and partial derivative of f with respect to y evaluated a b point times this variation. Okay, so this is, and we ignore higher order terms, right? We ignore higher order terms. So this can be written in this way. So this can be written partial of fx evaluated at a b, and partial of y okay, I don't write this. I will write this as a vector, right? So evaluated at a comma b dotted with u, vector u, vector u1, u2, vector u1, comma u2, and delta t is a scalar. Yeah, you can take out delta t. So it's a scalar. So delta t times partial of x comma partial of y evaluated at the point we are interested in is p. What are the point? A comma b, right? Started with the direction the traveler moves, right? So we give a notation for this one here. So partial of we give a notation partial of x, partial of y. This vector is denoted by this upside down triangle f, right? So this is called the gradient of f. So this is called gradient of f. Gradient of f is a vector, right? It is a vector. The x component is partial of f with respect to x, and the y component is partial of f with respect to y. So here, evaluated at this point, yep. So first find this, so this is called gradient of f, right? Very easy to find. So, all right. So according to our calculation, okay, gradient of f evaluated at So you have to plug this point into this one, right? Right, you get this value, then you get a vector, a constant vector, right? Started with the vector u, right? And this is the change in z direction. Okay, you have change in z direction. So what is the change in xy plane? Yep. Yeah. What is the change? Yep. So here initially is located at a comma b. Then you consider this delta t variation. Then his new position is a plus delta t u1. Yeah, that one. Okay. All right. So if you want to find the distance between these two, yep, you can find. So you know a comma b and this, this coordinate. Yeah. Then yeah, a comma b, one point, and the other point a plus. Yeah. Oh yes. Delta t u1 b plus delta t u2. Then how do you find magnitude of delta u1 delta t u1 squared delta t squared plus u2 squared delta t squared is common. So if this is a unique vector, right, this is equal to 1, then the change in xy plane is delta t. If this is a unique vector, so you just find the direction gives you, so just find the unique vector along this straight line. So it is given, right? So the horizontal change in xy plane is delta t. So let's divide, then you get, then the slope on the mountain at this point, roughly equal to, approximately equal to gradient of f, or gradient of f evaluated at p dotted the unit vector u. So if you if delta t, if this delta t is infinitesimal, infinitesimal small, so then this is equal to this one. Gradient of f evaluated at the point p dotted with the unit vector. So this is the directional derivative. How do you write the directional derivative of f in the direction u? So this is how. So there's that. So here we go. So directional derivative of f in the direction u, which is equal to this. This is the proof of that. I think you better remember this. Directional derivative. Gradient of f evaluated at the point dotted the direction u. So this direction, u must be a unit vector. Okay. So anyway, you can use chain rule to show that one, right? You can use chain rule. So how do you use chain rule? So basically here, so this is the Hiker's. So this one gives you, so this is the Hiker's path R, right? Okay. And if you know the function, so this is the function f, then you are able to find f of, yeah, so if, so yeah, so you can find the height of this path. So how do you find f of, yeah, so f of the x, let me check that. This path, yeah. If you consider this, yeah, if you consider this, yeah, this line segment, so now the traveler travels along this, yeah, this path, and this is the projection, OXY projection, right? Okay, yeah, so this is the path. Yeah, this one is the path. Is this one? Yeah, f of r would be, f of r would be the three-dimensional trial, right? Three-dimensional trial, right? So this path, basically, if he travels along the straight line, and if you, yeah, so if you plug, so that means if you can take the composition of f with that path, then you get this height. If you want to find the height along this path, yeah, you have to composite this one with this, right? Combine these two, then you get the height function, right? Got it? Makes sense? Because I have limited time, right? I try to, so yeah, so let's write that down. So f of r of t. So now our path is this straight line. Yeah. So, right, this is our path. So it is equal to, yeah, so this is r. R is the straight line. Uh, x f of, yeah, of that point A plus u1 delta t x component and y component b plus u2 delta t. And this is x component, let's say, so this is t, this is t, right? T, yeah, so yeah, so this is your x of t, and this is your y of t, and f is a function of x and y, and x and y is a function of single variable t. So d, now we use chain rule, df by dt is equal to chain rule, right? We use chain rule, df by dt is equal to partial, because here you have two variables, a partial of f with respect to x, and here you have single variable, then dx by dt, and you have another one, another path, f, now partial of f with respect to y, and d by, because this is a single variable, dy by dt. Yeah, this is chain rule, right? Chain rule. Yeah, So you know x and y function. X is a plus u1t. Let's differentiate that with respect to t. When you differentiate, this is a constant. Then when you differentiate a constant, you get 0. Then this is u1. This is u1. U1. This is u2. So you can write this one in vector form. Partial of f with respect to x, partial of f with respect to y, dotted with vector u1, u2. These are components of vector u evaluated at time t equals 0, because we want to find the tangent at p, right? At p. That's why we put 0 here. Evaluated at t equals 0. Yeah. Okay. This is evaluated at 0. You get u. Yeah. This the direction is u. So that's why you get that point. Evaluated at 0 is when you substitute 0 into here, you get p. Yeah, this is your point p. A comma b. So gradient of f evaluated at point p dotted with vector u. So you can use either chain rule to prove this directional derivative, or you can use Taylor expansion of higher dimension. So I use Taylor expansion. You don't need to, so don't give, don't ask proof of these kind of thing. Don't worry. So I don't ask these things. So you have to understand why, so how do you, find the gradient so this is the gradient. So this one is the gradient at this point P, right? So gradient. Make sense? So we have only 40 minutes to cover this up. Yep. Makes sense. Any questions? Now, so this is the notation. So directional derivative of f in the direction u, right? So this is the notation. Don't confuse this with this notation. Sometimes we no, all the time we use df for Jacobian matrix. Df. We use this notation for Jacobian matrix. I think you will use in third and fourth year, right? So don't confuse here. All the time you have u. So that's the difference between Jacobian notation and the directional derivative notation. So here direction is given u, right? So this is Jacobian notation and this is direction, right? Okay, let's do a small example. So this is the example. So find the directional derivative of this function. 1, 2, 3, and with this dependent variable, 4-dimensional. 4-dimensional surface. Because here how many independent variable? 1, 2, 3 independent variable and only one dependent variable, which is this. Let's say this is w. W is the dependent variable. So all together, so this is 4-dimensional curve or surface hyperplane. So at the point 1, 2, 3 in the direction, this time 3 dimension. Okay, let's find that. Okay, so what is the theory? Yeah, so you have to find the gradient of f first. So gradient of f, let's find that. Yep. So what is the definition? Yep. Gradient of f, because yeah, this is yeah, 1 2 3, there are 3 independent variables you have to find. So this is 3 by 3, 3 by 1. Yep. So first component is partial of f with respect to x, and second partial of f with respect to y, and third f with respect to z. Yeah. Yeah, let's find. Yep. So what is the partial derivative of f with respect to x? 2x. Now we differentiate this with respect to x, and other variables are considered to be constant, right? Yep. So 2x. Yep, only one x. Yeah, when you differentiate this with respect to x, this becomes negative 3y. Yes. And when you differentiate this term with respect to x, you get 0 because other variables are considered to be constant, right? Yes. Yeah. So this is first component. And let's find, yeah, so we computed this bit, and let's find partial derivative of f with respect to y. This term becomes 0 when you differentiate with respect to y. Negative 3x 0. Yeah, only negative 3x. Now let's find this component partial of f with respect to z. When you differentiate with respect to z, both become 0. You get 3z square. Yeah, so that's so this is the gradient of f, right? So which point we are interested in? Yeah, so direction derivative of f at this point. Okay, let's plug the point. Yeah. So gradient of f evaluated at point P. Yeah, point is given. Just throw these numbers for x, y, z respectively. X, yeah, 2 times 1. Yes, yeah, you can compute this. You get this constant vector. Yeah. So this is the direction, this is the gradient of f at point P, right? At evaluated at point P, right? Which is this constant vector. Okay, we computed that bit. All right. Remember this formula. You don't need to derive this formula. So you have to remember. So this is the direction. Okay. So we computed this bit. Okay. Gradient of f evaluated at point P. Yeah. So now we want to find the unit vector in the direction that we are interested in. Just so yeah, look at this. Yep, and find the directional derivative of f at the point P in the direction towards Q. Okay, so P is given. So P, we know P. Yeah, P is 1 2 3, and Q here. Now Q is 6 5 4, right? So can you find the unit vector in the direction of PQ? Yeah, very easy, right? You know these coordinates. You can find PQ vector. Yeah, very easy to find PQ vector. Yeah, everybody knows because you pass your A levels, right? If you are given these coordinates 1 2 3 and this is given, yeah, you can find PQ vector, yes, which is this. Then find the unit. How do you find? Yeah, you have to divide this vector by its magnitude. Magnitude is this. Divide its magnitude. Yeah, so this is the unit vector in the direction of PQ. Yeah, so we have that. So then, yeah, take take the dot product. Yeah, that's all. So dot product of this and that gives you the directional derivative. Yeah, pretty simple. If the hiker hikes this, yeah, this is not a, yeah, this cannot be visualized because this is a surface in 4-dimensional space. So we can visualize up to 3 dimensions. So this is not a surface in 3 dimensions. Yeah. So you cannot yeah, explain that one. Yep. So this is the directional derivative of f in the direction u. Yep. So pretty simple, right? Any questions? Move on. Yes. All right. So let's find the possible values of these directional derivative. So what are the possible values of these this directional derivative? So what is the maximum of this slope at a certain in the direction of u? So minimum. Can we find maximum and minimum? Yes, we can. So how do you? So because this is a dot product, right? Dot product between the gradient of f evaluated at the point and the direction u, right? So because of that, so you can use the definition of dot product. Yeah. What is the definition? Magnitude of u, which is 1, because this is a unit vector. Magnitude of gradient of f evaluated at the point, I will say evaluated at point. Yeah, it is. And cos theta, theta is the angle between this direction and gradient of f. Yeah, theta. So you know the max and min value of cos theta. Cos varies between -1 and +1. Therefore, directional derivative varies between where to where? Magnitude of gradient of f and negative magnitude of gradient of f. Right? So the directional derivative always varies between plus or minus gradient of f, magnitude of gradient of f. That is a very good concept, right? I hope this makes sense, right? Makes sense because of that dot product, right? And u is a unit vector, magnitude of unit vector is 1, and cos, you know the range of cos function, yeah, cosine varies between -1 and +1. So the directional derivative bounded between magnitude of gradient of f. Okay, does it make sense? Yeah, what is the maximum slope? Yeah, maximum if you have a power hiker, he has to take this path, this route, this path, this direction. If he wants to take a steepest, steepest slope, steepest uphill, he has to take, this direction, this slope. So this is the gradient at that point. Yep. So if you have a power skier, you know skier, right? If you have snow mountains, you can ski through the mountain, right? If you have a power skier, he wants to take the steepest downhill path, he has to choose the negative of magnitude of gradient of f. If you have a power hiker, he has to choose, yeah, this slope, right? If you have a power skier, he has to take, yeah, steepest downhill path. So this is the steepest downhill and this is the steepest uphill because the gradient or directional derivatives or gradient in the direction u varies between magnitude of gradient of f and negative magnitude of gradient of f. Yeah, as I said before, yeah, so these are the level curves and this is the height. So if you have a lazy hiker, right? Let's say he doesn't want to climb any mountain, right? So he has to take, let's say he is located here at this point. He has to take this path. Because he is very lazy. He doesn't like to climb any hill or so on. Yeah, if you move along this path, you don't need to yeah you don't need to climb any hills. It's a nice flat path because the height is the same on this path. So this is called your level curve. Yeah. So this is also another level. The height is 100. So if you have a lazy hiker, if he wants to avoid elevation change, so he has to take this route. Yeah. And if you have a power hiker, he has to take, so he has to take this gradient, so positive, magnitude of f. So he wants, if you have a power hiker, he wants the steepest uphill path. Let's say, this is the steepest. Yep. So he has to take this route perpendicular to this level curve. So look at the height. Height is increasing in this direction. So the power hiker takes this path. Yep. And power skier takes opposite side. Because so cos theta here if cos of 0 is 1, so when theta, so here theta varies from 0 to 2 pi or 0 to pi, right? 0 to pi or 2 pi. So maximum value 10 at theta equal to 0, right? Right. So if he wants to take a steepest uphill path, he has to take this route. He has to take this direction. He has to move in this direction. If you have a power skier, so he has to take this direction. Got it? So power hiker wants the steepest uphill path. Power skier wants the steepest downhill path. Lazy hiker, he will take this contour, this level curve. He will move along this level curve. The height does not change. Lazy hiker, so if he moves along the level curve, then what is the angle between u and, so this is u, the direction, and this is the direction of delta, no, gradient of f. So what is the angle between u and gradient of f? Gradient of the direction of gradient of f always in the direction f increasing. Here look at f is increasing in this direction, always perpendicular to the level curve, right? Gradient of f, this is very important, right? Gradient of f is always perpendicular to the level curve. So if you draw a tangent, so yeah, so tangent, that tangent is perpendicular to this gradient of f. So this guy, if this lazy guy is moving along this path and this is the velocity, yep, so this is, yep, this is the, let's say this, he's moving in this direction, right, u direction. So his movement is perpendicular to this gradient of f. Therefore, if you take the dot product of u and gradient of f at this point, yeah, so it becomes 0. The slope, yeah, gradient, yeah, the directional derivative of a lazy hiker is equal to 0. Yes. Yeah, this is important direction of gradient vector, right? Yeah. So gradient of f is always perpendicular to this level curve, to the contour. Yeah, to the contour. So this is the level curve. So gradient is perpendicular to the level curve. Yeah. And it is in the direction of f increasing. You can see f is increasing, height is increasing in this direction. So the direction of gradient is this direction, right? Okay. Yep. So if you have a power hiker, he always take this route in the direction of gradient of f. So angle between u and delta f is 0. If you have a power hiker. If so, yeah. So this is the, this direction. So this is the direction. So how do you find the, if you have this direction, how do you find the unit vector? You have to divide it by its magnitude, right? So this is the direction of steepest ascent. We call it steepest ascent. So this one is the steepest ascent or fastest increase. And if you have power skier, he has to take other way around, other side. So angle between u and delta f is pi. Cos of pi is -1, right? So he has to take the opposite direction, right? So this direction is called direction of steepest descent. Previous one ascent, steepest ascent, increasing, ascending order. Remember ascending, ascending, steepest ascent, descent, yeah, steepest descent. Mega duma, bæවුම Now downhill, වැඩිම downhill බෑවුම මේක. අපි කියන්නේ the direction of steepest descent. Fastest increase. Yeah. Yes, makes sense. Yeah, this is the concept, direction of gradient vector, which is always perpendicular to level curve, and it points to the side where f is increasing. So f is increasing in this direction. Yeah. So therefore gradient, the direction of gradient is this. Yeah. Yep. So let's do a small example, right? So yeah, so here you are given a mountain, the equation of the mountain. So it is given. This is a three-dimensional surface, right? Because it has two independent variable with one dependent, three dimension. Yeah. So okay, what is the direction of steepest ascent at point? Point is given. We are interested in this point and the level at this point. So this is the level height at this point height. So this is the corresponding level curve according to our concepts. So you can see here height is increasing in this direction. So the then gradient of f, what is the gradient, what is the direction of gradient of f? So it is perpendicular to this level curve. Okay, this is the tangent. And okay, then this one, direction of gradient of f is perpendicular to this tangent. Okay, and how do you draw this arrow? So we can notice our height is increasing in this direction. Then arrow is this direction. So this so this is the direction of gradient of f. So how do you find that? So you are given the function. So first find the first derivative. So a function is given, partial of f with respect to x, 2x, other term 0, and the second component, partial of f with respect to y, is become 0, 2y, 0. So this is so the gradient at this point you have to plug this point into this equation. So what is the point? Negative 3 comma 0. Let's plug that point into this. 2 times negative 3 is negative 6 comma 0. So this is the direction. So direction of steepest ascent. So what is the direction of steepest ascent? Tell me the direction of steepest ascent. Hurry up. All right. So this one is perpendicular to both steepest ascent and steepest descent. So this is tangent to the level curve, right? Tangent to the level curve. This one is tangent to the level curve. So this, there is no, I think, will not. So wait a second, I will explain. So as I said before, so sine of, so you can see if you have a positive one, so if you so let's say a is a unique vector, and so you are given the equation of this mountain, right? So this is the great tangent, how do you say, directional derivative of f in the direction of u, right? So if this value is positive, right? If this value is positive, that a points uphill, right? So gradient is if the gradient, so this value is positive, a points uphill. If the directional derivatives in this direction b is 0. So B should be the tangent to the contour, right? And if this directional derivative of f, the direction of C is negative, then C points downhill, right? So this is the summary, right? So here, this is, so this is the mountain here, real mountain, I think. And here, so here this red curve, and this is the starting point, I think. So this path is the steepest, steepest. So this is the path of steepest ascent. So if you move along this path, so you get the very difficult path to climb this mountain. So this is the top of the mountain, right? This is the top, and this is so somewhere below, right? So if you take this path, and this is the hardest path, you have a lot of power to climb this mountain along this path. So here you can see this is the path of steepest ascent. So if you are power skier, you have to go down in this direction. Yeah, power skier, and this is power hiker in this direction. Okay. Yeah, so I will summarize this last week. So we'll